Oh. No, well, I probably watched it when I was in like high school, but like 6 years ago or something. Yeah, it was the end. Yeah. I should go find it.
Thank you. I'm actually going to give you until Friday. Yeah.
Okay.
I mean, whatever you prefer.
Can we try and edit?
Something is wrong? Is it on?
That is it. I mean, I don't know. How do you guys feel about the homework?
I feel like I could go in a little more detail, but from the way what's being asked,
Yeah.
like I may not have to.
So you feel like you're probably going to get full credit, but you're not exactly sure why? Is that?
You didn't ask us to justify how we came up with the picture.
Or how detailed the resolution has to be.
Right.
Like you said, you don't have to put the matrices, but.
Right. Maybe I'll say a little bit more about it, and then we'll have it for Friday. By the way, so here's an announcement. So you've probably noticed that none of the algebra, combinatorics, geometry people have been around much this week. So we're all living in Palo Alto this week. I went and then I got really sick, and my intention was to come back and teach. But what I'm going to do is that I'm going to teach both today's class and Friday's class today. Very quickly. No.
Great.
No, so what I'm going to do is I'm going to teach a class now, and then at 2 o'clock I'm going to teach the other class. And if you can come, great. And if you can't come, then it's going to be online, and you can watch it there. But so, right, so two classes today. At 12 to 1 and 2 to 3. No class Friday. And then the homework, I'm going to let you guys turn it in on Friday, either by email or you can just leave it in my mailbox. So that's the plan. I hope some of you can come at 2, so I'm not talking to myself, but if it comes to that, I'll do it. So anyway. So, I mean, I was kind of debating whether to have the homework be due today or on Friday, and I could have gone either way, but maybe what I can do is tell you just a little bit more. I almost got to tell you everything that I wanted to tell you about the Hall complex. There was just one short thing that I didn't get to tell you, so maybe I'll tell you that, and we'll make this we'll make the homework due on Friday. And maybe we'll just talk about an example. So the point is basically that Hall complexes, as I'm sure you're aware of by now, are hard to visualize, right? The definition is some definition and it works, but if you actually want to visualize this, it's hard. But somehow in the artinian case, this is a little bit easier. So what I mean by artinian, So I'm a monomial ideal I is artinian if it contains powers of each one of the variables. So I think I mentioned this earlier. Okay. And maybe we'll actually do an example like, I don't know, x to the 7th, y to the 6th, z to the 4th, x to the 5th, y cubed, and x, y to the 4th. Okay. So then you're supposed to build this polytope, right? This polyhedron, I'm sorry. So we're going to make a polyhedron. And the way this is going to look is that you take some t. This is kind of physics notation, right? This means t is very large. And then you take these points. So for example, x to the 7th is in the ideal, so you need to put the point t to the 7th, comma 0, comma 0. Right? So maybe let me switch colors so I can. So those are the axes, x-axis, y-axis, z-axis. Okay. And so t to the 7th, 0, 0. Well, I don't really know what t is, but think of it as some large number. So t to the 7th is pretty far along the x-axis, okay? And I'll denote it 7, 0, 0, but I really mean t to the 7th, comma 0, comma 0. Okay? Then 6, 0, 0. Okay, well, that's a point that is along the y-axis, and it's not as far as this one is, right? So, I don't know, maybe it's here somewhere. 0, 6, 0. Then z to the 4th gives me a point 0, 0, z to the 4th. Question?
T to the 7th 0, 0 or T to the 7th 1, 1?
It's a very good point. It's t to the 7th 1, 1. Okay, I hope that doesn't ruin anything. So, no, that shouldn't ruin anything. Just think that this point is 1, 1, 1. Okay. And then the picture is the same. Right? So this is t to the 7th, 1, 1, 1 t to the 6th, 1, and 1, 1 t to the 4th. So something like that. Yeah. Then t to the 5th, t cubed, 1. Okay? So that means that you go t to the 5th. I mean, really, if I were to be drawing this to scale, and if t was really fantastically huge, then if t to the 7th is here, then t to the 6th is like right here, right? I mean, because t is up huge. Right? So if t is 1,000,000, then this thing is 1,000,000 times longer than this. So that means we won't see anything. But so you want to kind of imagine that this is really way farther out than the others are. So something to keep in mind. So t to the 5th, t cubed 1 is like you're kind of really farther out this way and then not as far out in this way. And so you're maybe over here somewhere. Okay. And then xy to the 4th, so you go t to the 1 in this direction, t to the 4th in this direction, and 1 in this direction. So you may be over here. Okay. And then what you're supposed to do is just make, out of all of those points, make these cones that go out. And so this polyhedron is something hard to see, and it kind of goes out like this. Sorry, 140. Thank you. And one thing to notice is that these 4 points are all on this plane, which is not the xy plane, but it's the x equals 1 plane, y equals 1 plane. Okay? And then you're supposed to kind of I think you guys already drew a picture like this, where kind of take these things. So that's the convex hull of these points, and then you look at everything that's kind of further out. Right? So I think I won't try to draw it. Just everything further out is what we call PT. Right? So everything that goes out in this direction, and this direction, and this direction. So for example, all of this stuff is in. Okay. So this is PT, and then we're supposed to look at the bounded part, at the bounded faces, and that's the hull complex. Right? The hull complex I is the bounded part of the bounded faces of PT. Well, it turns out that you have a special trick here that you can do in the artinian case, which is the following. I'm going to define Q sub t to be the intersection of P sub t with the simplex whose vertices are the point that you have on the x-axis, not really the x-axis, but the y equals 1, c equals 1. Anyways, basically the convex hull of the points on your axes and the origin, everything shifted up by 1. Okay? So this green thing I'm going to call, what name did I give it in the notes? Maybe delta of I. That's a terrible name. You'll see why today. So maybe I'll call it simplex of I. Okay. So I'm going to consider Q sub t to be, what is this really? What I'm doing is basically, I'm just taking this infinite guy and I'm truncating it at this green plane right here. Right? So what's the intersection? The intersection is going to look like something like this. So I hope you see this as a three-dimensional picture where all of these 4 guys are on a plane. And maybe I'll shade it orange so that you can see that it's this plane over here. So that's what I defined Q sub t to be. Okay. And the nice fact here is the following. So always Q sub t is an n-dimensional polytope. So really the only thing I'm saying here is that by cutting off right there, I'm making myself something bounded, which I think makes sense. Simplex of I is a facet of this guy. Again, I think that makes perfect sense because it's kind of the facet closest to you, right? But this is kind of the key thing here, the bounded facets of PT, in other words, the facets of the hull complex, are all facets of QT. And they are precisely the facets of Qt such that the inner normal vector is strictly positive. Okay. Question?
Yeah, the simplex I facet or the simplex front face facet?
Oh, yeah. Let's see. So what's a good way to clear out this notationally? I mean, so Brandon's point is that the simplex I is the n-dimensional thing, and the facet is only the n-1 dimension. So, I don't know. Let's call it let's call this guy the, I don't know, the outside face of I. Okay. It's a long name, but that's what I mean here. The outside facet of I is also a facet of Qt.
So just you make three little orange marks near the origin. Does that correspond to the shaded front?
So you're saying I made some orange marks?
Yeah, does that correspond to the shading? You're saying that little.
Oh, so actually, so you mean these three little? Those are. Yeah. No. Yeah. Good point. So really, maybe this deserves to be called 0, 0, 0, which really is the point 1, 1, 1. Yeah. A good point, because then I went and shaded this orange.
So what is that shading?
So what that shading corresponds to is that it corresponds to this face. So I guess it does kind of. I guess I shaded that brown already, so I should have shaded that brown over there. So let's be consistent. Let me unshade this stuff, because there's something I had shaded brown already, right? I had shaded this brown. So let's shade this brown. And this is the same thing as this. Okay. And the point is that this is the plane where z is equal to 1. That's what I mean by that shading. That's a horizontal plane. Okay. So what do I mean by an inner normal vector? Well, every hyperplane has two normal vectors, right? One going that way and one going that way. So if you have a polytope and if you have a facet, then you have two normal vectors, the one that's pointing into the polytope and the one that's pointing out of the polytope. Those are the inner and the outer ones. Okay? So I'm going to take this polytope that I have here, and I'm going to consider the inner normal vectors. Okay? So, for example, for the big face, what I call the outer facet of I, if you look at the inner normal vector that's pointing in that direction, in other words, all of its three coordinates are negative, right? Because this is the positive orthant. You're pointing in the exactly opposite direction. The three coordinates are negative. Okay. Now, as for the other guys, well, all of these other guys are kind of inside this orthant, which means that all of their inner normals really point in positive directions. Okay. So what I'll say is that all but the outer facet of I have greater than or equal to 0 normal vectors. Okay? But here I'm saying strictly positive. Okay? So if you look at these four facets that have a chance of being in the Hall complex, well, the thing is that this brown facet that I shaded, if you look at the inner normal vector, actually that's a vertical vector. Okay? And that means that one of the coordinates of that guy is 0. Two of the coordinates of that guy are 0, right? This normal vector is 0, 0, 1. And so that guy gets thrown out. Right? This guy has inner normal vector 0, 0, 1. But if you look at the other three faces, these are all tilted in a way that all their components are positive. Okay? So that means that the bounded facets of PT, the facets of the hull of I, are exactly these three facets. Okay? So this is hull of I. So that's the first thing that I want to say. Okay? And then the second thing that I want to say is the following. Imagine that you stand at this green point right here, the point 1, 1, 1, and from there you look at the polytope QT. Okay? So the polytope QT is over there, but you're seeing it as a surface, right? Because it's there in front of you, so it's three-dimensional, but you only see what's visible to you, which is the two-dimensional surface. Okay? Well, if you're standing here, what you're going to see is actually this triangle. It's kind of this triangle you're going to see there. And then you're precisely going to see the three black faces that I colored. But this bottom face is not visible to you because from this point, this stuff is flat. You can't see it. Yeah? So the three faces that you can see from this point are precisely the three faces of the hull of I. And that's how you can draw this picture, is if you somehow manage to visualize what it means to stand at this point. So if you stand at 1, 1, 1, what you're going to see is a subdivision you see a subdivision of this big triangle. And that is the hull complex. Okay? So if I'm to do this in this example, then I imagine that I'm standing over here, and what I'm going to see is, let's see, I've colored this green, so let's make it green also. So what does the hull of I look like? Well, I see this triangle. And I see it split like this. And so this is 700, 530, 140, 060, 004. Okay. And that is the hull complex. So you can always see it in one dimension lower. For example, if your ideal is three-dimensional, you can always see it as triangulating a triangle. If your ideal is in 4 variables, then you can see it as a subdivision of the tetrahedron. And so that buys you a little bit of room to be able to see something.
So,
Yeah.
so you're seeing, like, sort of, you're seeing a straight edge on the bottom. It's really just like relaxing between.
Right. So this is actually a polyhedral complex, right? So the vertices are these, and then it has 7 edges and 3 faces. And so, for example, right, so the point is that from here, actually, this flat line looks split into 3 pieces. Whereas the straight line, you do not see. So that's why this gets cut into 3 pieces. So that's how you can visualize this. And so in the homework, I asked you several things, but one of the things was to draw a picture like this. So. And just by looking at some of the pictures, it looks like that's what you did, but hopefully now you can compare what you did with how I just showed you, you can do this, and then hopefully these answers match. Okay. All right. Any questions about this? So I want to advertise something, by the way, that as you know, there's software that can help us with resolutions, things like this. And there is a great piece of software that allows you to visualize polytopes that you're having a hard time visualizing. I probably should have told you that before the homework, but, well, the homework is due on Friday, so you can still go to this thing, PolyMe. So you can just Google that, and you can find it. The problem is that it's hard to download, as I understand. But I know that I've used an online applet to draw polytopes, so this is out there somewhere. And Laura looks like she knows where to find it, so talk to her.
I remember it's only available on Linux and Mac, right?
No, but there's an online version.
The applet works.
And Chris O'Neill actually has installed it on his machine, so you can also ask him how he did that. Did you have a question?
Yeah, I was wondering if the facets of QT are necessarily lying in planes.
What do you mean exactly?
Like, if we had these, they're triangles, so they have to lie in a plane. But if we had like larger, like a hexagon, or
Hexagon,
something.
for example.
So are you asking me if these need to be triangles?
In the treatment in R3, are they lying on a plane? Or
Well, if you're going to draw a hexagon here, then that better be a hexagon on a plane. I mean, it really should be what you see. If you see it flat, if there's no weird shadows, then it's because it's flat, and that means you need to draw it flat. Why a hexagon? Okay, so that's the Hall complex. And the moral of this story is that any monomial ideal can be resolved. Let me write this down. So the moral of the story is that any monomial ideal in Rn in variables has a cellular resolution of length less than or equal to. That's the moral of the story of the Hall complex. And you can, to some extent, compute with this. Maybe a little bit hard to visualize, but you can do it. So our next goal is a little bit more ambitious, actually. The next thing that I would like to show to you is that any monomial ideal in m variables has a cellular resolution of length less than or equal to n. But now I'm going to ask for more. I'm going to ask that this be a simplicial resolution. Okay. So that means that your pieces are not allowed to be any polytopes. They have to be simplices. You can't have a hexagon. You have to have the two-dimensional things have to be triangles. Okay. So that's what we're going to do in the next two classes today. So let's just start with a bit of notation. Let's say that you have some simplicial complex and you have labels. So the vertex I is labeled by some monomial I, right? And then we know that what you do is that you take face F, and you have to what you do is that you label it by the least common multiple of, so for each vertex in F, you take all the vertices in F, you take their monomials, you take the least common multiple. Okay? This is what we've been doing over and over again. Okay? So, do this in an example. So this is a simplicial complex, and these faces are both full. Okay, they're both there, and I'm going to label the vertices like this: z squared, x squared, xy, and y squared z. Okay, so that forces a label on everything else, right? So for example, the edges get labeled like this should be x squared y, this should be x squared z squared, this should be y squared z squared, this should be x y squared z, this should be x y z squared, and then the two triangles also get labels, right? So maybe this one is what, x y, I think this is not going to show up in the video. X, y squared, z squared, and x squared, y, z squared. Okay. So that's a simplicial complex and the labels on all its faces. Okay. And then I take the complex that we associate to this thing, right? So we know what that guy looks like. It looks like you go from the faces. In this case, there's two faces. So two copies of the ring. Then you go to the edges. There's 5 edges. Then you go to the vertices. 4 vertices. And then, depending on whether you want to resolve I or R mod I, you either put an R here or you don't. I want to resolve I, so I'm going to write this sequence. Okay? Now, this is not just a sequence like this. There's a grading on this, right? And the way we do this is that we grade each copy of the ring by the degree of the corresponding face. So for example, these two faces, they have degrees 2, 1, 2, and 1, 2, 2. So that's what I do to the shifts here. I shift one copy of R by this, the other one by this. Okay. The edges here are shifted by x squared z squared is 202, y squared z squared is 022, x squared y, xy squared z, and xy z squared. And then these 4 guys are just 200, 002, 110, and 021. And this guy doesn't get a shift. So this is what I call, so this is delta. We've been calling this thing F sub delta, right? By the way, I want to be more explicit here. So what are the maps? For example, let's see. So let me give names to the vertices. So maybe I think this is going to disagree with how I did it in the notes, but that's fine. So we're going to give these names to the vertices. Okay. So for example, how do I describe the map from here to here? Okay, this is the boundary map that takes triangles to edges, right? So I need to say what I do to this generator and what I do to this generator. Okay? So for example, for this generator, 2, 1, 2, this corresponds to the phase 1, 2, 4. Okay? So what's the boundary of the generator corresponding to 1, 2, 4? Well, what you do is that you tell me what's around that, what's around there, what are the edges, right? But here, what I have to do is I have to do this orientation business. So for each phase, I have to decide how to orient it. So maybe I orient them both clockwise. And then I orient the edges. So let me orient them maybe as clockwise as I can. But here, okay. So I do this. Well, maybe let's do the opposite so it's a little bit more interesting. Okay? So this is the orientation. So what's the boundary of 1, 2, 4? Well, it should be something with E12, something with E24, and something with E14, right? But I have to choose signs. And how do I choose them? Well, remember what I do is that I put a +1 if my signs agree, and a -1 if my signs disagree. Okay? So for example, as I walk around clockwise, I see that 1, 2 agrees, so that gets a positive sign. 2, 4 disagrees, right? As you walk clockwise, you're traversing this in this direction, which is the opposite direction. So you get a minus here. And then 1, 4 gets a plus sign because it agrees. Okay? So that's the differential. But that's not quite the differential for the following reason. What is the degree of this thing? E1, 2, 4. The degree of E1 to 4 is 2, 1, 2. Right? And what are the degrees of the other guys? Well, the degree of 1, 2 is 2, 0, 2. The degree of 2, 4 is 1, 1, 2. And the degree of 1, 4 is 2, 1, 0. Okay? And this needs to be a homogeneous map, right? I should take something of degree 2, 1, 2 and send it to something that's homogeneous of degree 2, 1, 2. And so the way of doing that is basically by sticking monomials here that get you to the right degree. Right? This is degree 202, so it's missing a y. This has degree 112, so it's missing an x. And this has degree 210, so it's missing a z squared. So that's how this works. And this we call the Taylor complex. Okay. So this thing that we've done several times, we're going to call it the Taylor complex of delta. Okay. And remember, the point is we would like to know whether this resolves the ideal of vertices or not. And we know exactly when that's true. So this is just a reminder. This Taylor complex is a free resolution of the ideal of vertices, which in this case is I, where I is a vertex. If and only if each one of these delta less than or equal to m is acyclic. For monomials m. So this is just review. we saw this. Okay? Now, the other thing that I'd like to discuss is, if this happens to be a free resolution, then how do I know if it's minimal or not? Remember that our ultimate goal, if we can do it, is to find the minimal free resolution, which is unique. So when is that the case? So this thing is minimal if and only if the label of each, if you look at any phase and what its label is, and you compare it with what label you put on the phase minus an element of the phase. Okay, so here f is some phase of delta, and I is some element of that phase. Then these guys should have different labels. Okay. So that means that if what I did here is a free resolution, then I can tell right away if it's minimal or not. Is it? So you're supposed to look at this picture and compare the label on each phase with the label of its facets, and they should be different. So in this case, it works because actually you don't see any things that are labeled equal, right? Everything gets a different label in this picture, so that means that that condition is satisfied. Okay. So if we check this, which by the way you can check, so this is a resolution. You can check that this is true, and if you check this, which is true in this case, then you know right away that you have your answer. You're done. This is the minimal free resolution. By the way, so this thing is also a review, but it's review for something really, really old that we did. But if you go back to the notes from, I don't know, at least a month ago, we discussed how you had a minimal free resolution if and only if, when you looked at the monomial matrices, so let me write this down. In the monomial matrices of the resolution, so if you had a monomial matrix like this, whenever these two guys had the same label, the entry had to be 0. So this is basically what I'm saying here. If I have the same label on a triangle and on an edge, then I shouldn't have a differential there, right? Meaning that this edge should not be on this triangle. So we had already showed that this was how you could tell if a resolution was minimal or not. And so I'm just translating that into this language. Okay. So that means basically that it's easy to tell if this thing is minimal or not. Okay. So as I told you, this is our next goal. Okay. It's an ambitious goal. Start with any monomial ideal. And basically what I want to do is cook up some simplicial complex so that this procedure works. Okay, that's the plan. So for any monomial ideal I, so this is the goal. For any monomial ideal I need a labeled simplicial complex that will do it. Label simplicial complex delta such that f sub delta resolves I. Okay, that's our next goal. And what's our plan? How are we going to do this? This is going to be similar to what we've done in the past. So we're going to do it in 2 steps. So the first step is that we're going to do it for I, which is in a certain sense generic. Okay. And then the second thing is that basically we're going to reduce any case to the generic case. So first I'll tell you what to do. First I'll give you a procedure that almost always works, which is, remember when we did it for the 3-dimensional staircase, it was the same thing, right? I gave you a procedure that almost always worked. Basically, you just draw the Buchberger graph, and that'll do it for you. And then if that doesn't work, then you have to fiddle with it a little bit by doing these deformations. It's exactly what we're going to do here. Start with it with something that almost always works. And if that doesn't work, then you reduce it by deformation. Okay, so that's our plan. So first I'm going to tell you what generic means. So first say that a monomial M prime strictly divides a monomial M if, so first of all it should divide it, but second of all, so M prime should divide M, but the way that this should work is that if a variable appears in M, then it should not appear in M prime with the same exponent. Okay? So if a variable xi appears in M, then the degree of M prime in that variable should be less than the degree of xi. The degree of M prime in variable xi should be less than the degree of M in the variable xi. Okay. So, example, x squared y cubed strictly divides x to the 7th, y to the 4th, z squared, but x squared y cubed does not strictly divide something like, I don't know, x squared y to the 7th z, because even though it divides it, you have a 2 here and a 2 here. Okay. So that's what it means to strictly divide. And then I'm going to say that a monomial ideal, M1 up to MR is generic if the following thing holds. Whenever you have 2 monomials, MA and MB, that have the same degree in some variable, a positive degree. So this implies that some monomial MC strictly divides the LCM. Okay. So let's think about that for a second. what's the contrapositive of this thing? I'm saying, suppose this is not true. Okay? So no MC strictly divides the least common multiple of MA and MB. So that's exactly the condition to have an edge in the Book-Burger graph, right? Contrapositive says if you have an edge AB in the Book-Burger graph, that's exactly this thing that we said, right? That you look at the box, and there shouldn't be anything strictly inside the box. And being strictly inside a box means strictly dividing the top of the box. So the contrapositive says if you have an edge of the Book-Burger graph, then basically MA and MB can't have equal and positive xi degree. Okay. Now, if you remember, we had a definition of strongly generic. And strongly generic demanded this for any A and B. We said I never want to see an x squared and an x squared in two different generators. Okay? And here I'm saying I'm going to allow you to have an x squared and an x squared as long as you're not an edge of the Book-Burger graph. But if you are an edge of the Book-Burger graph, you better not have the same exponent in any of the variables. Okay? So this is weaker than being strongly generic. So that makes sense since we're only going to call it generic. So it is in this sense that I mean that for generic things, this is going to work. And otherwise, we're going to have to work a little bit harder. And this is the same thing as before, right? So this idea of the Book-Burger graph worked very easily if the ideal was strongly generic. And if it wasn't, we had to work a little bit harder. Okay, so given that, let me make the key definition, which is something called the scarf complex. The scarf complex delta I of a monomial ideal I which let's say it's generated by M1 up to MR is